Okay, this is the second and final video about time series. This time we'll be looking at seasonal indexes. In the last video, we were looking at random looking time series and trying to smooth them out in order to find any patterns lurking in the chaos. This time we'll be dealing with time series that already have obvious cyclical patterns. We can do some interesting things with this kind of time series, and it all has to do with something called seasonal indexes. But first, here is the data that we'll be looking at. We have daily pizza sales data for 4 weeks. And here is the graph of pizza sales versus time period. Looking at the graph, we can see a clear 7-period cycle. There is a consistent pattern that repeats every 7 days or weekly. We're going to calculate the seasonal indexes for this data set, and the first step towards doing that is to put the best fit line through the data. And in this plot, we can see the line and its equation. This line captures the long-term trend in the data. And we should take a quick look at the plot to make sure it's reasonable. And looking at this graph, it certainly looks like overall pizza sales are slowly increasing in a linear trend. It does not look like a parabola or any other nonlinear trend, so we'll keep this straight line equation as our best fit line. Next, we're going to calculate y hat for each data point. Here is the best fit line equation from the previous slide. Just remember that x is the time period starting at x equals 1. So here are the y hat values for each point. Next, we need to calculate y over y hat. In time series notation, y refers to the data, which is pizza sales in this example. So pizza sales divided by y hat gives us these numbers. For this next part, I find it useful to rearrange the data based on its cycle. For example, this data set has a cycle that repeats every 7 days, so I've broken it up into week 1, week 2, week 3, and week 4. For each time period, I have included its value of y over y hat that we found in the previous slide. Now we can start calculating the seasonal indexes. Each part of the cycle has its own seasonal index. We'll begin by finding the seasonal index for Sunday. To do this, we take the 4 values of y over y hat that are associated with Sundays. Then we average these numbers to get the seasonal index for Sunday. Next, we'll move on to Monday. Now find the 4 values of y over y hat that are associated with Mondays. We average them to get the seasonal index for Monday, and this pattern continues until we have the seasonal index for every day of the week. Here is the finished product. This table shows the seasonal index, which I have abbreviated as SI, for each day of the week. Before we get into the more advanced topics, we can make some basic observations about these numbers. A seasonal index is the average value of y over y hat. We can think of this as a percentage of y hat. For example, when we look at the seasonal index for Sunday, we see a value of 1.4037, which is around 40.4% above y hat, or the expected value of the long-term trend. So Sundays have pizza sales that are on average about 40% higher than what the long-term trend suggests. Mondays, on the other hand, have pizza sales that are on average about 48% below expected value or expected long-term trend value. And here are the rest of them. With this in mind, we can see how Friday, Saturday, and Sunday form the peak of each cycle, and Monday through Thursday forms the valley of the cycle. But let's move on to how we can use seasonal indexes. We're going to look at two of their applications, deseasonalizing the time series and making predictions in the future. In many ways, these two applications are opposites. Let's first look at deseasonalizing numbers. This is an attempt to remove the cyclical pattern from the data so that we can fairly compare different parts of it. To begin, I've shown part of the data set, and I've included the seasonal indexes for each day. To deseasonalize a data point, we just need to divide it by its seasonal index. So we just take Y, or pizza sales, and divide by its seasonal index to get these deseasonalized numbers. And we can plot them versus time as well. These numbers more or less represent pizza sales if we could remove the weekly cycle seen in the data. The point of this is to allow us to make fair comparisons between different parts of the cycle, or different days of the week. For example, suppose we want to compare Wednesday and Saturday in week 1. Just looking at pizza sales, we see 106 compared to 314. But that isn't a fair comparison at all. Saturday is fundamentally different from Wednesday when it comes to sales. But we can compare the deseasonalized numbers because this takes away the weekly cycle and puts them on an even playing field. Looking at these numbers, we can see that the restaurant is performing better on Wednesday than on Saturday. So although 106 pales in comparison to 314, 106 is actually pretty good for a Wednesday, and 314 is not that great for a Saturday. The deseasonalized numbers give us a way to compare different days of the week fairly. And let's quickly look at another example. Unemployment rates typically have a yearly cycle. For example, it is common for unemployment to be lower in the summer months as temporary workers find jobs on farms and tourist resorts. Let's suppose that these are the seasonal indexes for March and July, and let's use them to deseasonalize these employment numbers from last year. For March, we get 4.06, and for July, we get 4.36. So although unemployment dropped from 4.8 to 4.1%, the economy is actually slightly worse. There are a couple of ways that this is reported in the news. They might refer to seasonally adjusted unemployment, or they might talk about real unemployment. These are terms used when comparing deseasonalized numbers like this. Next, let's talk about the other main application of seasonal indexes, making predictions into the future. We're going to return to our pizza sales example and predict sales for the next week. That means we need to extend our time frame for 7 more days. The original data set ended at time period 28, or 4 weeks. So we just need to extend further out to time period 35 in order to add 1 more week. Next, we need to calculate y hat for each of these time periods. Here is the best fit line equation again. remember that x is equal to time period, and we get these values for y hat. The point of doing this step is to extend the long-term trend onto the future values that we are going to predict. Next, in order to complete our predictions, we need to add the weekly cycle from our original data sets. The process is essentially the opposite of deseasonalizing numbers. Instead of dividing by the seasonal index, we multiply by it. So here are the y hat values that we found in the last slide, and here are these seasonal indexes for each day of the week. We just need to multiply them together to get our predicted values for the future. So let's add these predictions to our original data set and look at the graph. The original data is in blue and the predicted values are in red. And it looks very reasonable. We have successfully extended the long-term trend and the weekly cycle to make a strong prediction for the sales 1 week into the future. Let me just make one quick comment on extrapolation. Predictions are less and less trustworthy the farther you go into the future. That's just common sense. And if you are interested in exactly how that works, then you can learn much more about this topic. We have really only scratched the surface. There is one more thing to mention, and that is making predictions for data that does not have a clear pattern. Let's return to the example from the last video on smoothing. This data set has no clear pattern, so seasonal indexes could not be used. And making any kind of predictions for this data set is pretty futile. But if you put a gun to my head and said, make a prediction for the next time period, then as a last resort, we can exponentially smooth the data and use our last smooth value as the prediction for the next time period. So let's exponentially smooth this data set. In the last video, we already tried W equal to 0.7, which was too little smoothing, and 0.1, which was too much. So let's try W equals 0.4 and find these smooth values. You can verify these for yourself. The last smooth value is about 66.2. So if I absolutely had to make a prediction 1 time period into the future, then I would just use this number. So here is a graph of the original data in blue and the exponential smoothing in red. And at the very end, I have extended the last smooth value 1 time period into the future in green as our predicted value. It is an extremely rough guess, but I guess it's better than nothing. Finally, we've reached the data set that you'll need to answer the 3 questions coming up. The data shows quarterly hotel occupancy rates for 3 years. If you sketch a graph of the data, then you will see a clear pattern you can use. So good luck with that, and I'll see you in class.